Swayam Prabha. Digital India. Educated India.
Hello friends, so we are back in the MOOCs course on fundamentals of nuclear power generation, and it's a quite hot afternoon outside at Guwahati, which welcomes you to the 12th and the last week of the course. Over last 11 weeks we have discussed about different aspects of nuclear power generation. Some of the modules or some of the weeks were quite theoretical in nature, like when we discussed about the fundamentals of the nuclear power generation, the source of nuclear energy, different types of nuclear neutron interaction, the fission and fusion reactions, etc. Whereas some other lectures or some of the other modules were more practical in nature, like different types of nuclear reactors we have discussed. We have discussed about the fusion technology, and also in recent weeks we have talked about additional factors like the safety aspects of nuclear reactors and also the radiation effects on living beings particularly. So, we have more or less covered all the aspects that you need to know to have some basic idea about the nuclear power generation, and only a small part that is left to finish up the course, which we are going to do during today's lecture and also the one that is going to follow. And to end this particular course, of course, we are going to discuss about something where everything ends, that is the topic of waste management. Waste, probably you are very much aware about with this term. It refers to something that is not having any kind of value, and therefore, we need to get rid of this. Similarly, in nuclear plants also waste definitely refers to the spent fuel and also quite a few other kinds of resources which we can't use for any further nuclear power generation, and hence we need to dispose that. Now, waste management not only for nuclear, but in any other kind of power generation also, that is of a huge concern. Like if you think about a coal based power station, the waste that we get from coal based power stations are fly ashes and the bottom ashes. Handling bottom ash is not that difficult, because we can convert the bottom ash to some kind of slurry form and then use some kind of hydraulic transport to take that to some kind of storage location. But fly ash is very difficult to handle. Like if you have experience of visiting any power station, thermal power station that is, or maybe in the neighborhood area, you will probably find that in a general size power plant, around, if we draw a circle, an imaginary circle of something like say 8-10 kilometer radius, taking that plant itself as the origin or the center, then you will find the entire area being covered by fly ashes. It is a real menace, the handling the fly ash. There are definitely lots of environmental regulations and protection acts which requires the plants to treat the fly ash instead of disposing that to the atmosphere. And different agencies are trying different kind of disposal, like some of the agencies are trying to make bricks out of those fly ashes. Some of the agencies are trying to use that fly ash for production of cements and similar kind of other materials. But just think about say 500 megawatt thermal power plant, coal based thermal power plant can produce a few tons of fly ash every day, and handling such huge quantity of waste is not a matter of joke. The additional factor in nuclear plant is that definitely we are going to have waste, but also we can't convert that waste to any kind of form like the bricks or cements that I just mentioned about, because they may have some kind of radioactive nucleus inside also. And therefore, even for the waste also you need to be careful about the possible radiation hazards it may cause, and hence we need some kind of special technology to store and dispose the nuclear waste. In fact, disposal and storage of nuclear waste is probably the most discussed about term whenever we discuss the probability of setting up in a nuclear power plant. Like there is a common notion among general public that the waste that we get from nuclear plants are of infinite life and they are going to lead to radiation hazards for infinity, which is actually not true. Again, from the very beginning, what I am repeatedly telling, that kind of notion can be partially attributed to the lack of knowledge. And in this module, whatever we are going to discuss, I am just going to touch upon different ways of managing the nuclear waste, and after understanding these concepts, probably you will be able to be in a good position to explain to the common public about what are the real hazards that nuclear waste can produce, and exactly what are the common practice that presently we use to curb such kind of menace. But before we go to the waste management issues, we need to remember a few points. These are points which are associated with those common belief of general public. Firstly, nuclear power is the only large scale energy production technology which takes full responsibility of all the waste and ensures that they are all properly disposed of, which is not done by any other kind of power stations, be it coal based thermal or be it gas turbines or whatever. They always leave a huge amount of waste to the environment without bothering about the environmental regulations. But in nuclear, 100% of the wastes are taken care of. The amount of waste generated by a nuclear power plant is also very small compared to other thermal electricity generation technologies. This is somewhat related to the amount of energy that we get from say 1 gram of uranium and 1 gram of coal. We have compared it very early in our course, and we have seen that the energy that we get from the same quantity of these two fuels, from uranium or from nuclear fuel, we get something of the order of 10 to the power 6 or 10 to the power 7 times larger than what we get from coal. Correspondingly, the amount of waste production also will be significantly smaller from two plants of similar capacity. The nuclear fuel or nuclear waste rather, which comes out, that can also be used as a resource. By the breeding technology, we can always convert some part of this nuclear waste to generate some further fuel. Like earlier we have seen the reprocessing and replenishment technologies that we use. By virtue of that, we can always recover a part of the spent fuel to produce new uranium oxides or even sometimes the MOOCs, the mixed oxides. And also certain cases the nuclear waste can be used for some other kind of applications as well, some other kind of industries, sometimes for research purposes. So, whatever comes out of a plant, everything is not waste, rather that can also have some kind of values or technical values, I should say. Nuclear waste is neither particularly hazardous nor hard to manage relative to other toxic industrial wastes. Lots of industrial plant uses some kind of hazardous chemicals, some very corrosive acids or alkaline agents, and just dispose of that to the environment, maybe to the corporation sewage systems, maybe to the river, which leads to huge amount of environmental pollutions. That is not at all valid for a nuclear power plant, because the chemical effects are minimal, and also even the radiation effects also can properly be taken care of. And finally, the disposal method for high level radioactive wastes are very well developed. As per the modern technology, we are in a very good position to handle the high level radioactive waste. What we mean by high level, I shall be coming shortly, but for the moment you can consider that the strongest possible radioactive waste or the most hazardous radioactive waste also can be taken care of properly by the present day technology. And also there is international consensus about which one to use and which one is not that much suitable, how to treat different kinds of waste materials. There is a good amount of consensus. Geological disposal is generally considered to be the best option. We shall be coming to that shortly. So, whenever you are discussing or you are participating in any kind of discussion regarding the management of nuclear waste, these are the points that we should always remember. And try to stress upon that it is not that the waste that we get from nuclear power plant are going to cause huge amount of public issues. Now, what do we mean by radioactive waste? In order to know the sources of radioactive waste, we also need to know what we are referring by this particular term. Here, by using the term radioactive waste, we are referring to the materials which contain certain portion of radioactive atoms, but the radioactivity level of those atoms or the combination of those atoms are so small that does not have any kind of potential from nuclear industry point of view or even from research point of view as well. So, the radioactive waste definitely contains some amount of radioactive nucleus, which can go for further radioactive decay, thereby releasing both ionizing radiation and also energy. But the amount of radiation that we are getting from these waste materials are not at all of significant amount. They doesn't have any kind of they don't have any kind of potential to be used as any kind of nuclear fuel or even in any other industries also. Then only we are calling that as a waste. As long as it has even the smallest possible potential available, we would like to use that. So, radioactive waste may be just natural substances such as uranium ore residues with certain radioactive isotopes of radium and radon. It can also contain some fission products, some products which has very high neutron capture cross section like those neutron poisons. It can also contains isotopes of those like cobalt and plutonium, and definitely fission products can be there. Fission products themselves are radioactive in nature, so they can go through series of radioactive decays to get converted to some kind of stable isotopes at the end of the chain. Now, radioactive waste we can get from different stages of the fuel cycle and also from a few other possible sources. Like mining of uranium is probably the biggest source of radioactive waste. We shall be coming to that shortly, but you can get the idea. Say if you are talking about coal, from the mine we do not get the coal directly. It is not that whatever we harness from the mine that can be directly fed to a coal based power station or any other application where coal is used. Rather, we generally get coal coupled with rocks and some other kind of materials. So, by using some kind of chemical or mechanical treatment procedure, we have to separate out the coal and then only we can apply that to the industries. And the same is applicable to any kind of nuclear fuel like uranium as well. Lots of unwanted material that also comes out during mining, and that constitutes a large fraction of the radioactive waste. Next is the fuel processing and fabrication part. From that uranium, earlier you have seen the fuel cycle. After mining we go through the process of enrichment, and after doing the enrichment we go for the production of fuel itself. During this entire processing period we can have lots of different kinds of nuclei produced which can act as radioactive waste. The operation of the reactor itself, which probably from our visualization point of view the most common kind of waste, this is just the counterpart of the ash that we get from a coal based plant. That is, once we have loaded the reactor with certain amount of fuel, say certain type of fuel, maybe say natural uranium only, at the end of the process, while initially there was 0.7% uranium 235, at the end of the process or end of the operation of the reactor also you will find there will be small fraction of uranium 235 left. But that amount may be so low that it is not going to affect significantly the operation or operating zone, or also it is not going to, it is not suitable enough to harness some kind of power from that. So, we need to get rid of that, and that also can be a very high level radioactive waste. The reprocessing and recycling of the spent fuel, during the reprocessing also we get lots of isotopes being separating out which may be radioactive in nature. And final decommissioning and dismantling of plant. Once the life of a plant is over, like earlier we have seen the generation 2 reactors are expected to have a life period of 40 years, some of them are still working to something like 50 years, whereas the generation 3 reactors are expected to have a lifespan of something around 60 years. But once that lifespan is over, then the plant needs to be completely dismantled, and during this dismantling procedure there is a large chance of spreading of radioactivity to the neighboring areas. Now, next is radiopharmaceuticals. We have already seen how the medical industry is increasingly depending on radiation based sources. Earlier we used to have only X-rays through which the radiation was used, but now there are several other kind of techniques also where radioisotopes are regularly used. And whenever we are using those kind of radiation based medicines, at the end of the process that also will lead to some kind of radioactive waste. Next is the radionuclides, which are used in some other industries and also for research purposes in different research labs, and the nuclear weapon program, which is probably the biggest source of the most hazardous radioactive nucleuses or nuclei that we can get. Finally, the cleanup of contaminated site, like if we have done some kind of accident involving some kind of experiment, I should say, involving nuclear material or using some kind of radioactive nuclei, or if there is some kind of, because of the where kind of situation, if some nuclear weapons are employed to some certain kind of places, then at the end of the day we have to clean that, so that the common human life is restored. And to do that, we have to clean up the contaminated side, and during the cleanup process also the persons who are involved in this cleaning operation may get affected by the radiation, and also the entire neighboring areas also can get accepted or can get affected. These are certain isotopes which are commonly found in the radioactive waste. Some of them are very long lived fission products, and some of them are medium lived fission products. Here one important thing, the unit of this half life is MA, where MA refers to mega annum or 10 to the power 6 annums. So, whatever number we are getting in this column, that need to be multiplied with 10 to the power 6. Like iodine 129 is having a half life of 15.7 10 to the power 6 years, which is an extremely long period to talk about. But there are certain other isotopes which are having a smaller half life, like this particular isotope of tin is having a half life of only 0.23 years, and cesium 135 can have 2.3 into 10 to the power 6 years. Sorry, tin 126 is 0.23 into 10 to the power 6 years. Also the mediumly isotopes which half life are smaller than this. Some of the mediumly isotopes, here the unit is year itself. So, like krypton 85 is having a half life of only 10.76 seconds, whereas even the longest one in this reach is 151 samarium 151, which is about 96.6 years. And as per the generation 3 concepts, the expected life period of a nuclear plant is something around the range of 60 years. So, you can see apart from the last one, all of them are having a life period within that. Next, we need to classify the radioactive waste. Different countries use their own method of classification, like the way radioactive wastes are classified in US, that is quite different from the way it is done in UK. But to get a more generalized idea, actually in all these different classification process you will find similar kind of terminologies used, but the way they are quantified, that can be different. But to avoid any kind of confusion, we are following the classification proposed by IAEA, that is International Atomic Energy Agency, which is the international body related to the atomic energy, and it has several nuclear powered countries as its member, including India and United States and UK. So, the classification IAEA has provided, according to that we can classify radioactive waste into 6 categories, and the first one of them is exempt waste or EW. This is the waste which can be treated just as normal waste. The radioactive effect that we may have from this kind of waste materials are well below the corresponding clearance limit, and therefore, they can be treated just like we treat the fly ash from a coal based power plant. Next is very short lived waste. It involves the waste which contains radioisotopes which decays over a very short period of time. That is, the half life of these radioisotopes may be in the range of just 1 or 2 years, and therefore, within limited period of a few years they can completely get destroyed, and subsequently this short lived waste material will get converted to the exempt waste. That is, we need to provide a quite small period of containment, during which all the radioisotopes present in the waste material will get decayed to a stable nuclei, and then we do not need to provide any further containment, it can be treated like normal wastes. Then we have very low level wastes. Very low level wastes refers to those kind of waste materials which does not meet the criteria of exempt waste, but also it does not need a high level of containment and isolation, and therefore, we can dispose it with quite less amount of effect. So, radiation dose is there, but the radiation dose that is coming out from this very low level wastes are generally very small, and therefore, quite close to the ground, we are quite close to the surface of the earth, we can dispose this waste with while following certain regulations. Generally, this kind of waste involves soil and rubble of with low level of activity concentration. And the concentrations of long lived radionuclides in VLLW are generally very limited. This now we have the low level waste. This low level waste probably comprises about 90% of the total radioactive waste that we may have. But the radiation dose that is contributed by this very low level waste, that is just of the order of 5% of what we have globally from the radioactive waste. So, under this low level waste category, we can have several kinds of isotopes with limited half lives. They go through the containment procedure for a few 100 years, and then we can dispose these containers in a near surface facility quite similar to the very low level waste. A broad range of waste comes under this category, which includes, which can have both kind of options. It can have short lived radioisotopes with very high level of activity, whereas it can also contain long lived radioisotopes with quite limited activity, and generally that is measured by this kind of parameters: 12 gigabecquerel per ton of beta gamma activity. That is, during the radioactive decay of the corresponding radioisotopes, it will go through either beta or gamma decay, or maybe both together, and the total amount of radiation that we are receiving from this should be less than 12 gigabecquerel per ton of beta gamma activity. Sometimes it is also written as 4 gigabecquerel per ton of alpha activity. That is, whatever amount of energy release or radiation dose that we get corresponding to one alpha radiation, in terms of that, if we compare 4 gigabecquerel per ton of energy that will be released by this low level waste. Next is the intermediate level waste. These are again the waste that requires a greater degree of containment isolation than that is provided by the near surface disposal. However, their temperature is independent of their temperature, or I should say the energy released by them are generally quite small to be considered, and therefore, this intermediate level wastes are considered, or the storage, the way we treat this intermediate level waste, those storage were designed only considering the radiation effect, but not the thermal effect. Generally, the heat dissipation is limited to 2 kilowatt per meter cube, or 2 kilowatt per unit volume of the waste material, and as long as the radioactive effect is significant, but the thermal energy release is less than this, we can call that an intermediate level waste. And finally, we have the high level waste, waste with level of activity concentration high enough to generate significant quantities of heat by the radiative decay process, or sometimes the waste with large amount of long lived radioisotopes that need to be considered in the division of. Disposal facilities need to be properly designed, and now the near surface disposal will not work, rather this kind of waste need to be disposed several 100 meters underground. The total volume of high level waste that we get may be just about 3% of the total radioactive waste, or the high and intermediate level waste that combine to something like 10%, where remaining 90% comes from low level waste or very low level waste. But the total radioactive dose that we are getting, maybe this high level waste itself can contribute more than 60%. Now, this is a nuclear fuel cycle. This is a diagram which you have seen earlier also. This refers to different kind of processes the uranium goes through since the mining of the uranium from the core or from the ore, the mines. Now, fraction of uranium that we get from the ore is very small, typically of the order of 1% by mass. In certain cases, it can be as high as 20%, but generally it is less than 1%. And the mechanical and chemical treatment is done in the milling. So, for the mining, it goes through the milling process. You have learned again where it receives some kind of mechanical and chemical treatment, and that uranium is separated in the form of uranium oxide U3O8. This is conventionally called the yellow cake, which you have heard earlier also. And the yellow cake, the concentration of uranium can be as high as 80% or even higher in certain situations. Huge quantity of residues left after milling is known as the mill tailings, which generally is a sandy waste material. So, this is the first kind of radioactive waste that we are getting. Actually, the term mill tailings is a quite common term related to any kind of mining activities, whatever left in the mine after getting the targeted material is can be called a the mill tailings. But here we are talking about a radioactive mill tailings, and hence we need to be careful about handling this mill tailings. But the issue is that total amount of uranium in core is very small, but due to this residue process we can increase the percentage of uranium in that yellow cake, that is that UF6 to something as high as 80 to 90%. Sorry, I am not sure exactly I told the correct thing or not, that is why I am repeating again. So, the uranium that we get from the ore, the fraction is quite small, less than 1% typically. It can be as low as something like 0.3%, but after processing in the milling we get the yellow cake where its concentration can be more than 80%. But what is left after this milling process, that is from here, that is what we are concerned about, which is the mill tailings. Mill tailings comprises of about 5% of the original uranium and the daughter products of uranium decay chain, mainly uranium 238, because in natural isotopes at least uranium 238 comprises more than 99% of the total volume. So, as more than 99% is uranium 238, so most of the isotopes that you get are because of the decay of uranium 238 itself, something like radium 226, radon 222 and certain isotopes of polonium, they can all appear there. Accordingly, it carries more than 85% of ore's original radioactivity. And also there can be several kinds of process chemical residues which were used during the chemical procedure during the milling process, and also a wide range of heavy materials. Certain long lived isotopes such as thorium 234, it has quite, or I should say short lived, their half life is quite short, like for thorium 234 half life is something like 24 days. Therefore, they can decay very quickly and just after a period of 24 days or maybe a month. So, during their procedures over this period of say 1 month, their radioactive effect is completely gone, and then its total level of radioactivity can get reduced to 75% of the original volume. Certain other isotopes like uranium 234 and thorium 230 have very long half life of the order of 10 to the power 7, 10 to the power 8 years, and hence their radiological effect will last forever. And this is another source of or another significant source of radioactive waste disposal or radioactive waste generation, I should say, that is a heap leach recovery process. While conventional uranium is harnessed from the ore, sometimes the stones which are supposed to contain small amount of uranium, or I should say instead of stone, certain slabs of stones with very small uranium fraction are put in a pile like this, they are heaped into a pile like this, and then some kind of acid is supplied on the top. On the effect of the acid, some portion of these rocks that melted and that comes out through this part into the collection basin, and from the collection basin that goes through three kinds of. So, after the heap leach process is done, we get a liquid, or we get two different kinds of liquid, one which can be rich in uranium, but the other one which is having a significant amount of waste material is left there. As the ore is crushed during the conventional milling process, the size of the particles will be quite small, of the order range of 70 to 75 micron. But in this process, we are thinking about just harnessing the material from slabs, and therefore, while during the milling process we can get size of the order of a few microns. Here the sizes of the particles will be much larger, something in the range of 20 millimeter, and these piles are also left above the ground on some prepared permeable pads. So, they can have severe kind of radioactive damage. These are the different types of tailings that we can get. The sand and slime based tailings generally come from the milling process, and the liquid one comes most from the heap leach technology. As you can see here, the most important part for the sand based case, the total radioactivity that is involved is 26 to 100 picocurie of radium 226 and 70 to 600 PCI of thorium 230. Whereas, when you compare that with the liquid thing, then the total level of radioactivity that we are getting is 20 to 7500 picocurie of radium-226 and 2000 of picocurie of thorium-230. So, there is a significant level of difference in the radioactivity that is contained by the corresponding mill tailings, and hence the way we dispose the sand or slime type of mill tailings, that has to be different with the way we treat the liquid ones. These are the possible hazards that we may have from the tailings. We can have radon acceleration, gamma radiation, the trailing material can get blown away by the dust. Accordingly, the dust wherever it falls will spread radioactivity there. The failure of the dam lead to spreading of radioactivity again because of some flood or any kind of natural calamity, and also the tailing materials or corresponding chemicals can seep through this bottom surface and can get absorbed into this area. There are several very hazardous elements like uranium and arsenic that can seep through this and can go to the groundwater, thereby getting spread to the entire community. Radon particularly is extremely dangerous to have. These are the different ways radon can enter a house and then cause different kind of radioactive effects. Particularly the effect of radon is to cause carcinogen, that is cancer, and such kind of carcinogenic disease are actually increasingly common. Like this is a data from United States, where we can found that the amount of people dying because of the lung cancer caused by the radon is more compared to the number of drunk driving. So, it is definitely a very big concern to deal with. Arsenic is another particle of consideration. Arsenic 74 can decay in either direction. It can either suffer an increase in the atomic number. Accordingly, we can have the formation of selenium 74, or we can have formation of germanium 74, depending upon what kind of reaction that is happening. And the effect of arsenic on the community can be classified into two categories: oxidative DNA damage and assessment of activation of transcription factor can lead to the alteration in the gene expression, whereas the oxidative DNA damage can lead to chromosomal aberration and also interface with cellular signal. All of them are leading to carcinogenicity, and therefore, the radiation effect from arsenic should be very carefully captured. The gamma rays, I could have shown this slide earlier also in earlier module, but this one I kept here. Gamma ray, again, they are generally introduced to the matter in three different ways depending upon its own energy level. Like when the energy level is small, we get photoelectric effect. Like the gamma ray is coming, it is striking one electron and transferring entire of its energy to the electron, so that the electron can go out of this atom with the same amount, or out of this nucleus I should say, with the same amount of energy the plasma supply has. The second case is quantum scattering. Here the energy level of this incoming photon, X-ray photon is shown here, but the same is applicable for gamma photon also. Here it transfers a part of this energy to the outgoing electron and it continues as a photon of lesser energy, which we call the quantum scattering. And finally, the pair production, when the energy level is quite high, then the photon, when the energy level is quite large, then it can lead to the formation of one electron and one positron. Now, electron and positron both are having extremely small mass of the level of 10 to the minus 31 kg or 10 to the minus 4 AMU. So, this electron and positron formation from this photon, which we are calling pair production, is an example of energy to mass conversion. And also the photon that we are having here, that need to have sufficiently high amount of energy so that it can go for this electron and positron formation. Like here we can write this interaction as gamma leading to the formation of minus 1 E0 plus 1 E0, where minus 1 E0 refers to the electron, this one refers to the positron. And therefore, the mass that is getting produced, if we do the calculation, then total corresponding energy has to be something like 1.024 MeV or 1.02 MeV, and hence this photon must have at least that level of energy, so that we can have this pair production phenomenon. This graph shows the possibility of different each of these three phenomena depending upon the energy level of the photon. When the energy level is low, it is the photoelectric effect which is more dominant. When the energy level is high, we can have the pair production to be dominant. Compton effect is dominant more or less in this in between portion. So, similar to radon, we can have also problems with the gamma ray radiation, and also we can receive significant amount of environmental effects because of arsenic and also uranium. So, considering all these effects, we have to be definitely very careful to while dealing with this mill tailings. And another factor to consider here is the large volume of tailing that we are getting. So, while the concern, as I am repeatedly telling, while the amount of radioactive effect that these tailings are correspond to is quite small, maybe just about 5% of the total effect that we get, but still the volume of the tailings consumes more than 90% of the total waste material, and therefore, we have to be very careful about how to dispose that. Earlier, they need to be disposed to any kind of location without being bothered about the corresponding radiation effects, without being bothered about putting any effective containment, and generally some kind of topographic depressions were employed, like say a valley behind a dam or dike, a custom built ring dike, a mined out pit from where all the material has been taken away, and therefore, the pit needs to be filled up with something, and mill tailings were also used there as a part of that something. The custom built pit or repository can also be an option, and underground mine can be an option. Even in a live mine also, you may have lots of empty spaces which or lots of empty tunnels which we can fill up. We need to fill up with some kind of material. So, there also the tailings can be employed or used to get employed, and the deep lake or river. But as time goes on, we kept on getting more and more information, and also had a better idea now about what we should do to or exactly how we should dispose these tailings. So, from there came the concept of this tailing pond. The tailing pond is generally the large structures where the uranium mill tailings are generally deposited. But while selecting one tailing pond or designing a tailing pond, there are several factors we have to be careful of, like the required storage capacity for the tailing and waste rock. Of course, it is just not for 1 year that we are going to store it, we are going to store it for a few years, and so the total storage capacity corresponding to the entire lifespan of the reactor should be considered. So, another can be site availability. The location for this should be quite close to the uranium mines, otherwise there will be chances of spreading of radioactivity because of transportation. Hydrology and hydrogeology can be a factor, as the water that is flowing in the local areas should not pass through the tailings, otherwise this water itself will get contaminated. The initial cost we would always like to be low, and the ease of operation is definitely needs to be considered. Finally, the geotechnical and geological conditions can also play a big role. And at the end, we have the complete engineering design, which will design the tailings, design the mill of and also the entire uranium circuit. If all this can be combined together, then that can lead to a very, very efficient methodology of tailing disposal. Present day methodology corresponds to tailing management facilities called TMF. These are isolated locations from where the tailings are kept for a very, very long time. They are generally located within mined out open pits or in surface impoundments, which is the geographical features and man-made barriers. These are the new, this is the new factor that is coming in, because even before even earlier days also, even before also, this kind of mined out pits or surface impoundments were in use. But nowadays, these man-made barriers or man-made protection systems which are introduced to keep the tailings within a certain boundary, and also to restrict the corresponding radiation effects. The groundwater and surface water also needs to be diverted from the tailings to prevent any kind of contamination. This is one possible kind of design, where you can see the water is there and the tailing is below the water. At this particular portion, we shall be having some kind of separation, so that the water does not come in direct contact with the tailings, and the waste rock from the bottom surface, and then water is also allowed to flow through the tailings in order to take the heat generated inside the tailings, and then that can pumped out for some kind of treatment. Their tailings are always deposited underwater to prevent them from oxidation, as it is not allowed to come in contact with air, so it does not get oxidated, provide shielding from radiation from the tailings, and also as the water layer is there, so even the dust is not allowed to flow away from the surface of the tailings. Tailings are deposited in the TMF as a slurry. The solids settle in the TMF while the liquids are later collected and processed through a water treatment plant to remove the contaminants. The resulting effluent must meet regulated quality requirement before it is allowed to be discharged into the environment. This is a possible flow sheet for this effluent treatment. The effluent that we are getting, that goes through a series of reservoirs. Each of the reservoir has its own role, like in this portion radium is separated, Mn is precipitated in this particular portion, pH is corrected in this particular tank. Accordingly, the effluent is allowed to go through series of chemical actions, and so that finally what comes out or what is going to the tailing ponds is much more safer compared to what we have started with. And along with the tailings, we also have something called the waste rock, because when you are harnessing the uranium from the ore, from the mines rather, along with the ores, lots of rocks also will be coming out, and some of those rocks will be clean rocks, where some others will be mineralized rocks. So, we have to get rid of this waste rocks also. The clean rock can be used for construction activities such as the construction of roads, etc., whereas this mineralized rock, it can be used depending upon what kind of mineral content it has. It can be used in certain chemical industries or in similar kind of industries, or it can be deposited on impermeable pads also. Seepage and runoff from the mineralized waste rock piles are collected and processed through a water treatment plant to remove contaminants before they are released to the surrounding. So, both waste rock and effluent requires treatment, but the treatment methodologies are generally quite standard. So, this is the typical nature of these tailing ponds. As I have mentioned earlier, we may have water in these portions and then the tailing below, and you can see these particular cross sections, how many layers are there. There are several layers of protection to separate out the water and the tailings. This table shows the composition of all this water. This is just for your information, so I am not going to detail of this. You can take a look at this table and get a better idea about different layers. But what is important is these tailing ponds can have three kinds of designs: upstream, downstream, or center line, depending upon the orientation of successive dams. In all the cases, the dam starts with a starter dike or starter dam. In all the cases, the first one is a starter dike or starter dam, which is the starting point, and then on top of the starter dam we add more and more dams. In case of upstream dam, if you look carefully, we are moving into the upstream direction, means more and more dams are towards the inner side, whereas in case of downstream direction we are moving towards outer side, and again dams are proposed in that direction only. In case of the upstream dam, while we are going in the upstream direction, in case of downstream dam, as you can see, we are moving in the downstream direction, whereas in case of center line we are moving straight upwards. So, different dikes are added, and as we are continuously adding dikes, we can change the height of this, but each of these three categories have their own advantages and disadvantages from construction point of view. Like the upstream one generally is quite low cost, as we are adding the upstream side. So, just by adding this dike we can keep on increasing, but the issue is the height can be limited, and also on what is below this second dike, that is only unconsolidated slimes, which takes some time to consolidate. So, the structure can be can have its own issues, particularly if it is subject to some kind of earthquakes. The downstream side trailing dams, here this is the starter one, and see how we have built the second one or the third one on top of them. This is definitely much more stable design, a very safe design both from static loading and seismic loading point of view, but the issue is the total volume of the dam or the amount of sand required to raise this dam wall. Here like if we go back to the upstream design, all these number 1, 2, 3, all of them look more or less the same, and therefore, the material required for each successive dikes are more or less the same, which is not true. Here whatever is the volume of the starter one, the second one is having slightly higher volume, third one is having even higher volume. So, as we keep on adding more and more layers, the volume is increasing, accordingly the cost will also be increasing. And last is the centerline tailing dam. Here the volume requirement for can be quite large, whereas the total space requirement also will be quite high. Whereas in case of centerline dam, as we are moving straight upwards, it can be raised quite quickly and smaller sand volume required compared to the downstream trailing volume, but unstable slope can develop in the newer structure for this. So, each of them has their own advantage and disadvantage, and all the 3 types of tailing ponds are in use, all the 3 designs are in use in different parts of the world. But of course, the designer should be very careful about choosing the type of dam they are going to use. Total expected volume of radioactive waste, say from 20 years from now or 30 years from now, also should be taken into consideration. So, today's lecture I am keeping up to this, where we have discussed more about the tailing ponds or different kinds of nuclear waste classifications we have done, and tailing ponds. Now, can you guess under which category these tailing ponds are falling? They are definitely low level wastes. May not be a very low level, but definitely low level wastes, which are very high in terms of volume, but very small or very I should not say they are insignificant, but the total radioactive dose is quite small. So, in the next lecture, which is going to be the final lecture of this course, we are going to discuss about the other types of radioactive waste, particularly the intermediate and high level radioactive waste and their possible methods of disposal. So, thanks for your attention for the day. See you in the next lecture.